In order for devices on a network to communicate, they need to know the address of the other devices. In most HPC systems and in our virtual lab, that network addressing is managed by the Internet Protocol. For standard IP networking, we will focus on Internet Protocol version 4, also known as IPv4, but we still need to cover some other underlying concepts. At a very basic level, devices on a typical HPC network will have both a hardware address and a TCP/IP address, which we sometimes call IP address for short. The MAC address stands for Media Access Control Address, and it consists of 6 hexadecimal pairs, leaving us with over 250 trillion unique addresses. MAC addresses typically include OUIs, which are organizationally unique identifiers that are reserved for manufacturers. So you can typically tell what company or manufacturer a hardware device belongs to from its MAC address. Nowadays, IP addresses come in 2 formats: the more widespread yet older IPv4 address and the newer, less adopted IPv6 address. For the scope of this course, we will not be talking about IPv6, so that means whenever we talk about an IP address, unless we explicitly state otherwise, we will be referring to the IPv4 address. An IP address consists of a 32-bit number that is usually represented in dot decimal notation, consisting of 4 octets, that's 8 bits in an octet, of the address. Since a 32-bit integer value is unique, there are many ways to represent that same IPv4 number, but the most common practice is similar to the example shown here. While there are 2 to the power 32 possible addresses, which equates to just over 4 billion, around 300 million are already reserved for special addresses, such as private networks and multicast addresses. Given the relatively low range of IP addresses that are actually available, it becomes a very real probability and definitely a problem when 2 IP addresses overlap. To illustrate the point, imagine we told you that the address belonging to the CHPC was 15 Lower Hope Road. It might make sense to you in your context since you are also in South Africa. But for someone living in England, they would find a very different 15 Lower Hope Road if they looked it up. So on the face of it, having 2 places or people reporting the same address can lead to some confusion. Much the same can occur in a network that does not account for IP address conflicts. Let's take a quick look at how IP addresses are represented so that it can help us to understand how to read them. I just need to mention that these addresses listed here are not public and they're not global addresses. They're made up of a private address. By definition, a private network is isolated from the world, so you can actually have 2 private networks that share the same IP addresses for different devices. But because they are private, they will never ever talk to each other, so they will never experience a conflict between their 2 networks. Now, following on from the previous example, when we take an IP address, the leftmost numbers are the most global scope, and the rightmost numbers are the most narrow scope. So in our examples, it starts with a country, then a city, then a district, then the actual building. This might seem counterintuitive to how we would describe an address, but it might help to understand it like you're starting a very broad search and you're slowly narrowing down your search. Given the syntax of the IPv4 address, we can see in this illustration how the various components can help you understand some details about that address. By looking at the 192 portion, we know that it's South Africa. If we see a 192.168 address, we know that it's referring to South Africa, Cape Town. 192.168.123 would be Rosebank, and then if we have the final part, the host ID, we'd know even the building number. Likewise for the United Kingdom, 172 would be the UK, 172.16 would be England, 172.16254 would be Sale. Having a side-by-side comparison here shows how the bottom line of each table has a conflicting address name, but as you broaden the scope, you realize that they are very unique addresses. This is the benefit of using a 4-octet system to describe the address. You have some ability to be a lot more descriptive with the number representation of the address than you do with the actual wording of the address. Now, you didn't think you'd get past this entire chapter without at least one quiz, did you? So for a quick recap, how many bits are there in an IPv4 address? And how many octets are there in an IPv4 address? And the answers are 32 bits and 4 octets, broken down like this. In actuality, it's a long 32-bit number that has been mostly arbitrarily divided into 4 octets, but it does make it much easier for human readability. In a standard 8-bit address pool, we usually refer to the final octet as the host address, because it will define the actual number of the machine in that network. It will define the actual number of the machine in that network, much like you would a house number for a street. The leading or leftmost octets are the network address, or perhaps the street name and not the house number. The net mask is a mechanism to perform a bitwise AND operation with the 32-bit network address to strip out the host portion of the IP address, that's the least significant part, and resolve only the network address. In this example, we are effectively removing the final octet because the net mask at that point is defined as 8 0 bits, and anything ANDed with 8 0 bits will result in zeros. The rest are all ones, which means that you take what is originally there and you output it there. This results in us learning the actual size of the available IPs for that network because we know how many bits are remaining. In this case, there are 2 to the 8 remaining IP addresses available for hosts because the leading bits take up 2 to the 24. Imagine a public network such as an airport Wi-Fi. Well, okay kids, believe me, there was once a time when we had these things called airports with these things called airplanes, and you could actually fly to places and you didn't have to stay locked in your houses. Anyway, I digress. So anyway, this public Wi-Fi probably gets hundreds or thousands of new devices connecting every day. If each device takes an IP address, there would soon be no more IP addresses available for any other devices that join. This is solved by using a pool of IP addresses that are dynamically allocated to devices. Then after a short period of time, they will expire. Again, this might solve the large number of random devices that join and leave the network, but if you have a mission-critical system whose IP address should not change, and it should not run the risk of potentially having that IP address taken away, you would want to hard code that IP address. So there are two types of IP addresses in a network: the static IP address, which is hard coded, and the dynamic IP address, which is temporarily allocated. In an HPC cluster, you would certainly want your management server to have a static IP address. And typically you would also assign a static IP address to every node in your system, but that is not necessarily required.